Good morning, everyone. Our ability to manufacture and to innovate in semiconductors is absolutely critical to maintaining global leadership in the industries of the future and to maintaining America's competitive advantage. With President Biden's CHIPS and Science Act investments, we are now in a position to bring leading-edge chip manufacturing back to the US. That keeps us in the lead today, but what about tomorrow? This is a diagram of a sliver of a chip that we designed in my lab about 5 years ago. So now, of course, it's considered old tech, right? But it's still confoundingly complex. So this sliver is about the width of a hair, a human hair, and zooming in a lot, you can see the transistors sitting down at the bottom. This is where the semiconductor materials are, where all the computation happens. But you also see all these many, many layers of metal routing for electrical signals. You see insulator layers separating the metals. There are billions of transistors on every chip, hundreds or thousands of chips on every wafer. And we need atomic level precision across a 12-inch diameter wafer. That's over 10 billion atoms across. Innovation in semiconductors is very, very challenging to improve performance of our chips, to keep at the bleeding edge of computation in this global competitive landscape. Right? It's a monumental task. Every new material, every new process that is introduced affects every other step in this chip. That affects the entire wafer, and that affects the entire foundry. Imagine if, in just a couple of years, instead of decades, we could create new generations of high-performance materials for semiconductors that also address pressing and concerning sustainability problems. Imagine if that advance enables US semiconductor manufacturers to sharpen their edge in this fierce competitive industry on a global scale that is so critical for our economic and national security. Today, new semiconductor materials begin in the lab with physics-based models. Scientists then have to figure out how to synthesize or to make these materials, okay, through a whole suite of experimental tests. All the sample materials are then measured and analyzed individually through a series of different metrology tools. And those experiments are then used to refine the material's design, and the process can start over and over and over. Every step here is lengthy, it's expensive, it's labor intensive, and when all of that is done, the material then has to go through further qualification, validation, certification to make sure that it's compatible with the other thousands of steps that are in the semiconductor manufacturing process. To get to volume production, tools that are already in existence may need modification. New tools might need to be engineered. The entire process from materials innovation to adoption can take decades, but we really don't have that time anymore. We are in a fiercely competitive space. There's growing concern over availability of materials, and we are desperate to transition to more sustainable semiconductor manufacturing writ large. This entire process needs to accelerate by 10x, if not more, down to just a couple of years. Fortunately, a paradigm shift in materials innovation has been brewing over the past decade, fueled by exponential advancement in AI and in autonomous experimentation. So AI opens up the aperture for new materials, but it also helps distill down to those few materials that have the highest likelihood of success. Then, the combination of AI and robotic labs allows for continuous feedback between the experiments and the materials design to further refine future experiments, accelerating the entire process through this AI decision-driven iterative cycle. So that really intractably hard problem with so many parameters is all of a sudden approachable. AI provides the researcher with the opportunity and the tools to co-design and to co-optimize, from materials to transistors to packaged chips. All right, so what is it going to take to realize that vision? Well, there are still fundamental research and prototyping to perform. Okay? We need to also set up secure data infrastructure with IP protection. We need to build up good data on bad materials and failed fabrication steps to train the AI. And we need to develop an infrastructure for autonomous labs and to make it widely accessible. And through all of that, we need to consider how all of this translates to production, and industry has to be a key player from the beginning. In fact, we need national level mobilization and buy-in in order to make this a success. And I'm looking at all of you for that. There are some hurdles to overcome: collecting and sharing data on materials and processes, of course, but creating standards and managing proprietary content. We need capital investment in autonomous labs, and we also need to build in verification and validation directly into the experimental cycle. There are also potential societal risks that we need to consider. Most critically, what if these systems create dangerous new materials or chemistries? Rigorous standards will need to be set up for vetting outputs that are built into the AI models that then define materials design. And that will include markers for toxicity, for environmental impacts, and other hazards as well. The Materials Accelerator Aspiration, when successful, is going to allow us to engineer and to deploy new materials on the order of years rather than decades. We'll see materials for semiconductors that are co-optimized not only for performance, but that can now address important issues like supply chain resilience and, critically, sustainability, both for existing and known materials, but potentially for new materials that we've not even thought of before. This competitive and edge and continued innovation and leadership in semiconductors will keep our factories running. They'll provide cutting-edge medical solutions to families, and they'll keep our soldiers safe in the field. And ultimately, this platform, the labs, the software, the talent pool that's driving it, are going to be able to port over to other sectors beyond microelectronics. And going full circle, we're going to be able to build better, faster chips for even more powerful AI. Thank you.